A rectangle with dimension 7 by 8 is shown in figure A. What is the perimeter? The perimeter of this, well, this side is 7, so this side is 7, that side is 8, so the perimeter would be 7 plus 8 plus 7 plus 8, and that is 30. A 3 by 1 rectangle is removed from one corner of a 7 by 8 rectangle as shown in figure B. What is the perimeter of this figure? So in this one, we've got to figure out the side lengths. Okay, well, this side here is going to be 8 minus this 1, so that's going to be 7. And then this side here will be 7 minus this 3, so that's going to be 4. And then add these guys up. So 7 plus 8 plus 7 plus 3 plus 1 plus 4. And when you add those up, I believe you get 30 again. Interesting. C. A 4 by 2 rectangle is removed from one corner of a k plus 4 by k plus 2 rectangle as shown in figure C. Suppose that the perimeter of figure C is 56. Determine the value of k. Okay, so a little bit different this time. So a lot of these are labeled. That's labeled, that's labeled, that is labeled, and so is that. So we have to figure out what's the label here. Well, that's going to be this k plus 2 minus this 2. So that's just k. K plus 2 minus 2. And then this guy here, this side, is going to be this k plus 4 minus this 4, which will be, again, k. Okay, so now the perimeter is going to be k plus 4 plus k plus 2 plus k plus 4 plus 2 plus k. And they're saying that that all equals 56. Okay, so if I do this correctly, 1, 2, 3, 4, that's 4k. And then add up the numbers, 4, 2, 6, 4, 2, 6, so that's 12. 4k plus 12. Hopefully I didn't make any mistakes there. And then we got 4k is equal to, what is it, 44, and therefore k is 11. And finally we have D. 4 by 7 rectangles are removed from the corners of a square having side length 8n plus 1 as shown in figure D. Determine the largest integer n for which the perimeter of figure D is less than 1,000. All right, so the same story. Let's see, do I need to label anything? I think I do, right? Because I got to label this guy. Okay, well, so it's 8n plus 1 minus this 7 minus that 4. So 8n plus 1 minus 7 minus 4. So that looks to me like 8n minus 10. Is that right? Yeah. Okay. So this is 8n minus 10. And then this guy here, I think it's the same story because you're going to minus a 7 and a minus a 4. Yeah. So that's also 8n minus 10. And I think it's the same thing here and here also. Okay. That makes it easy. 8n minus 10 and 8n minus 10. All right. Great. And then everything else is labeled, right? So let's add all this up. So we got 4 of these 8n minus 10s. Okay, that takes care of this, 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 and this. And then we have what it looks like to me, 4 of those 7s. So this guy, that, that, and that. And then finally we have 4 of those 4s, which are this, 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 and this. And I think that takes care of all the sides, I believe. And all of this, they want it to be less than 1,000. Okay, and then we got to figure out the largest value of n. That n is an integer. Okay, so this is 32n minus 40 plus 28 plus 16 is less than 1,000. So 32 and what is that all? Plus 4, I think. Yeah, minus 1,000. And then 32n less than 996. And then divide through by 32 and you get n less than 31.125. So therefore, the largest n, since n is an integer, is going to be 31. And that completes number 1. Rope is fed into a machine at a constant rate of 2 meters per second. The machine can be set to cut off one piece of rope every t seconds for various values of t. For example, if the machine is set to make one cut every 5 seconds, then 12 pieces of rope are cut off in 1 minute. If the machine is set to make one cut every 8 seconds, how many pieces of rope are cut off in 10 minutes? All right. So we have 2 meters per second right here. That's sort of the main piece of information. And then to me in this question, it's 10 minutes. Okay, so 10 minutes, we got to convert that to seconds. So we have 600 seconds because we're talking in seconds, so we got to convert it to seconds. And then 600 seconds divided by this 8 seconds will give me how many cuts have been made, I believe. And that's 75 cuts. And I think, is that all? How many pieces of rope? 75 pieces of rope. I think that's it, right? So for some reason, is there more to this question? Let me just see. 2 meters per second times 600 seconds is 1,200 meters. Okay, but what are they asking here? How many pieces? Okay, so just asking for pieces. Okay, they're not asking for a length yet. All right, whatever. Moving right along. If the machine is set to make one cut every 3 seconds, what is the length of each piece of rope? Okay, so I guess it's a continuation here. So we have still the 600 seconds, and then every 3 seconds there's a cut. So that means there's 200 cuts, so 200 pieces, I guess. And then that's when this information comes into play here. Now we have to figure out the length. So the full length is 1,200, and there's 200 pieces. So then we have to divide 1,200 by 200 to get the length of each piece. And that would be, I believe, 6 meters. Okay. C, if each piece of rope that is cut off is 30 meters long, determine the number of cuts that per minute that the machine is set to make. Okay, so a little bit backwards this time. So again, the full length was 1,200 meters, and each piece was 30 meters. So that means there was 40 pieces. Okay, and then there's 600 seconds. 600 seconds, but there was a cut every. There was every 40. This 600 has to be divided 40 times, basically, since there was 40 cuts. So divided by 40, and then you get 15 seconds. So basically what that means is that there was a cut made every 15 seconds. And they're saying cuts per minute. So if there's 15 seconds for one cut, in 1 minute, there would have been 4 cuts. Correct? So that's basically 4 cuts per minute. And finally, if the machine is set to make 16 cuts per minute, determine the length of each piece of rope that is cut off. Okay, so 16 cuts per minute. So that means 3.75 seconds per cut, right? You just take 16 divided by 16. And then we have 600 seconds, and then we have 3.75 seconds per cut. So that means that makes it 160 cuts, or 160 pieces. And then finally, you take the 1,200, which is the total length of the rope, and divide it by 160 pieces, and you get 7.5 meters is the length of each cut. Tania lists the positive integers in order, leaving out the integers that are multiples of 5. Her list is 1, 2, 3, 4, 6, 7, 8, 9, 11, 12, 13, 14, 16, 17, and so on. How many integers has Tania listed just before she leaves out the 6th multiple of 5? Okay, so for part A, it's still, the numbers are small, so we can kind of just list them. So it won't take that much time. 1, 2, 3, 4, 5, when we leave out the 5, because we're going to leave out all the multiples of 5. 6, 7, 8, 9, leave out the 10. 11, 12, 13, 14, leave out the 15. 16, 17, 18, 19, leave out the 20. 21, 22, 23, 24, leave out the 25. And 26, 27, 28, 29, leave out the 30. Now at this point we can stop, because just just before she leaves out the sixth multiple of 5. So the sixth multiple of 5 is 30, right? 1, 2, 3, 4, 5, 6. This is the sixth multiple of 5. So basically what they're saying is, how many numbers did you write out? And those are the numbers that I'm writing out. Well, 4, 8, 12, 16, 20, 24. 24 is the answer to that number, that question. Remember, you're only counting these guys. You're not counting the multiples of 5. Those have been left out. I wrote them here just to kind of, illustrate that they have been left out, but you're only counting the non-multiples of 5. Part B, if the kth integer in Tania's list is 219, determine the value of k. Okay, kth integer. All right, so we got to do a little bit of thinking here. Okay, well, here's the thing. Actually, let me just explain it with this guy, and then it'll be, I think, easier for you to understand. Let's say I told you that the 24th integer is 29, which it is. And I said to you, actually, a better way of wording it would be if I said, let's just word it exactly. The kth integer in her list is 29. Determine the value of k, right? I'm just explaining it from this. Well, what you need to really understand is that you're listing everything except the multiples of 5. So you have to figure out how many multiples of 5 are there before that number. Well, in this case, our number is 29. And then just divide by 5 and whatever integer value you get. So you just take the integer value. That's what that symbol means. Well, 29 divided by 5 is 5 point something. 5 point, whatever it is, 5.8. So the integer value is 5. So that means you left out 5 multiples of 5. This guy, 1, 2, 3, 4, 5, which is exactly correct. So that means that we have a situation where you have to subtract those 5 from some number. Okay? And what is that number? Well, my question at least, gave it to you. It's 29. So 29 minus 5 is 24. And they're saying that, in my question, that the kth integer is 29, or my 24th integer was indeed 29, right? Because we were only counting these guys, and in the previous question, we had counted that this was indeed the 24th integer in that list. So going back to the same question, this guy here, they're saying this time is 2019. So you use the same philosophy. You take 2019 and you divide by 5. And of course, we're looking for the integer value, and that's going to be 403. So that means those 403 multiples of 5 have been removed. So of the 2019 numbers, we have to not count those 403 multiples of 5. And when you take those out, you get left with 616. So that means that the 616th number is going to be 2019. And because these 403 multiples of 5 had to be taken out and were not listed. And this guy here, determine the sum of the first 200 integers in Tania's list. Let's start off with a simple example. Let's see if we can make this question a little bit easier. So instead of the first 200, let's say I said, find the sum of the first 20 numbers. 2, 3, 4, leave out the 5. 6, 7, 8, 9, leave out the 10. 11, 12, 13, 14, leave out the 15. 16, 17, 18, 19, leave out the 20. 21, 22, 23, 24. Is that the first 20? 4, 8, 12, 16, 20. Yes, it is. Okay, so if I have to add up the sum, I would just add them 1 plus 2 plus 3 plus 4, and then 6 plus 7 plus 8 plus 9. You guys get the idea. ... all the way until the very last group, 22 plus 23 plus 24. Now, we're doing this manually because there's not that many numbers, but the next guy here 200, that's too long to do manually. But here's how you would do it. Now, this would be easy if it was consecutive. It was just 1 to 24, because you guys remember that formula. If you have consecutive numbers all the way till n, there's a nice formula that it's n times n plus 1 over 2. Correct? But this is not consecutive. We're missing the 5s. But what we can do is we can add them like they're consecutive, like 1 plus 2 dot 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 all the way till 24, and then subtract from them the multiples that have not been included, which in our case were 5, 10, 15, 20, these guys. And I think that's it, right? I think that's it. So this guy here, we can just use this nice formula. So that would be 24 times 25 over 2. And then this, factor out the 5, and that would give you 1 plus 2 plus 3 plus 4. And then this, I believe, is 300. And then here, again, you can use this formula to do that. So it's going to be 5 times 4 times 5 over 2. And then this looks to me like 300 minus 50, which is 250. Okay, so that's basically how you would do this. So let's do it for the 200. So now we have to find the sum of first 200. Okay. So probably going to use the same sort of philosophy as before. Before, my example was just the first 20, right? And we had 20 numbers. And if you divide by 4, that means you'd had 5 sets of 4 numbers, right? This was right up here. You had 1, 2, 3, 4, 5. 5 sets of 4 numbers each. And therefore, you also had 5 multiples of 5, one for each set, 5, 10, 15, 20, and 25. But be careful, this last 25, we didn't count because we just stopped right there. So basically what that means is that this really goes just till 24. That's very important. So our numbers really went from 1 to 24, which is exactly what we had here. See, 1 to 24. This is 24. This is 24. So if we're talking about the first 200, same kind of thing. We have 200 this time. We're going to have to divide by 4 to figure out how many sets. And this time it's 50 sets of 4. 50 sets of 4. And then for each set of 4, there's going to be a multiple of 5. So there's going to be 50 multiples of 5. There should be a 5 there. So 5, 10, all the way till the 50th multiple of 5, which is 250, right? But remember, we're going to stop right before the 250, so our numbers are really going from 1 to 249. And that's really the most important thing to figure this out. Okay, now that we got that, the rest is the same. We're going to add up all the numbers from 1 to 249. But remember, we have to subtract from that the multiples of 5, which are going to be 5 plus 10 plus 15, all the way up until the last multiple of 5, which would be 245. We're not going to count that 250 because we stopped before we write that. Okay, so this should be pretty straightforward, as long as I don't make any mistakes with that formula, n times n plus 1 over 2. Okay, so the first one is going to be 249 times 250 over 2. This one here, let me factor out a 5 first. 1 plus 2 plus 3, all the way till what, 49, I think? Yeah, 49. So this is going to be, this 249, let me just put that 125 for now. And then 5, this is going to be 49 times 50 all over 2. Okay. Moving right along, 249 times 125, I believe, is 31125. And this whole guy, 5 times 49 times 25, 5 times 49 times 25. So that's 31125 minus 6125. And that is a 25000. Okay, very nice even number. And that pretty much completes number 3. A Schonk sequence is a sequence of positive integers in which each term after the first is greater than the previous term, and the product of all terms is a perfect square. For example, 2, 6, 27 is a Schonk sequence. Since 6 is greater than 2, 27 is greater than 6, and 2 times 6 times 27 is 324, which is 18 squared. Therefore, a perfect square. If 12x and 24 is a Schonk sequence, what is the value of x? Well, according to basic criteria, 12 times x times 24 would have to be some perfect square. Let's call it m squared. Well, this is 288x, and that's got to be m squared. Okay. But we also have to keep in mind that x has to be between 24 and 12 in order for it to satisfy that criteria. Okay, so what I'm going to do is... Since there's not that many, you can just test out individual values, 13, 14, 15, all the way till 23. That's one way of doing it. Yeah, that's definitely one way of doing it. And you can sub those in and see, but that's probably a very time-consuming way. Even for this, that's quite a few numbers. So what the better way, in my opinion, is to break this up into its prime factors. So, for example, 288 is equal to 2 to the power of 5 times 3 to the power of 2. So this is 2 to the power of 5 times 3 to the power of 2 times some x, and we want to be a perfect square. Now, this can be a perfect square if the exponents are even. So exponents are even. Okay. How can I make the exponents even? Well, if this x had a 2 to the power of 1, that would add with the 5 to give us 6. That would make it even. Now, this is already even. So how about I just make the x 2? Well, I can't because x has to be between 12 and 24. Okay, so let's keep going. If I add on a 3, I can't put 3 to the power of 1 because that with this 2 would be 3 to the power of 3. But I could put a 3 to the power of 2. And that would make it 3 to the power of 4 and make it even. So that basically would mean 2 to the power of 5 times 3 to the power of 2 times 2 to the power of 1 times 3 to the power of 2 is equal to m squared. And this combines to give 2 to the power of 6 times 3 to the power of 4. And this is indeed a perfect square because these exponents are even. Now, what I've chosen for x, let's see, what does that equal actually? 2 times 9, which is 18. And is 18 in that range? It is. So therefore, x is 18. So as you can see, a little bit of trial and error will be sufficient for these kinds of questions. Part B, if 28, y, z, and 65 is a Schonk sequence, what are the values of y and z? Okay, so a little bit different this time. We got two variables to work with. So we got 28, then we have y, z, and 65. And all right, so we got to do this whole thing again. Now, the other criteria is that when you multiply them all, it's going to give you a perfect square. So let's do that. Okay, what is 28, by the way? 28, in terms of its prime factors, it's 2 to the power of 2 times 7 to the power of 1. And 65 is what? Just 5 times 13, right? So when you combine this, you're going to get 2 to the power of 2 times 5 to the power of 1 times 7 to the power of 1 times 13 to the power of 1 times this y and this z, and this has got to be m squared. Okay, oh boy. All right, so I should be able to do this here. And then, of course, we've got to keep this in mind that 28 is less than y, which is less than z, and less than 65. That's also a criteria. All right, so where do I go from here? This is going to be trial and error, basically. Okay. Well, first of all, in order to make this a perfect square, I've got to make the exponents even. So this y and z, we've got to have at least a 5 to the power of 1 to combine with this guy to make it 5 to the power of 2. We've got to have at least a 7 to the power of 1 to combine with this guy, and at least a 13 to the power of 1 to combine with that guy. That would make it a perfect square. Okay, so that's great, but then I have to figure out individually what is y and z, keeping in mind this criteria. Okay, so if I made y 5 times 7, that'd be 35, but then z would be 13. Okay, that's no good. If I made y 5 times 13, that's no good. How about if I made y, Let me write these options out here. If I did 5 times 7 for one guy, see, all of these have to be greater than 28. That's why I can't use individual numbers. That's 35. 5 times 13, I believe, is 65. And 7 times 13 is 91. Okay, so, yeah. Well, that's not going to work, though, because no matter what, you're going to end up with an individual number, and all the individual numbers are less than 28. Okay, so what do I do now? The only thing I can think of is that we're going to have to add on something to this. So let's add on something small. The smallest perfect square is 4, right? Well, it's 1, but 1 won't help with anything. So let's add on a 2 to the power of 2. And then let's see here. I think that might work. So then I'll make one of these 5 times 7, which is 35. And then the z, I'll make the 4 times 13, which is 52. Yeah, that works because it satisfies this inequality. And then it makes this a perfect square right up here. Because this combines with that. That is 4, which is even, makes it a perfect square. And then this combines with that. This combines with that. And this 13 to the power of 1 combines with that. Yeah, that's it. So again, a little bit of trial and error. So y is 35 and z is 52. Determine the length of the longest Schonk sequence, each of whose terms is an integer between 1 and 12 inclusive. This means that your solution should include an example of a sequence of this longest length as well as justification as to why no longer sequence is possible. Okay, so the longest that you can make before we test it out to see if it actually qualifies would just be all the numbers multiplied together, all the numbers from 1 to 12. Now, I'm not sure if this will actually be a Schonk sequence because one of the criteria is that it has to be a perfect square. Well, this is essentially just 12 factorial, and 12 factorial is 479,001,600. Now, this is not a perfect square, so where m is an integer. So length 12, let's just write here length 12 is not possible. Okay, let's try length 11. But before I try length 11, because I have to know which one of these 12 I have to eliminate, right? So what I'm going to do is instead of writing 1, 2, 3, I'm going to write them out as prime numbers. So instead of 4, I'm going to write 2 to the power of 2, 5. 6, I'll write 2 times 3, 7. 2 to the power of 3, 3 to the power of 2. 10 will be 2 times 5. 11 is just 11, and then that's 2 to the power of 2 times 3, I believe, right? Yeah. Okay, so then when you combine all of these guys, it's 2 to the power of 10 times 3 to the power of 5 times 5 to the power of 2. Yeah. Well, see, this 7 and this 11, I am not going to count because if I put a 7 in there or an 11, there's no way it will ever be a perfect square because the exponent has to be even. And this is obviously 7 to the power of 1, 1 is not even, and 11 to the power of 1 is not even. So those have to be eliminated. So what I'm left with, let's see here if I did this correctly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so that's correct. Then 1, 2, 3, 4, 5, that's correct. and then 5, 1 5 here, 1 5 here, yeah, 5 to the power 2. So this is what I'm working with here. And this is indeed a perfect square because all the exponents are even. It's basically just 2 to the power 5 times, oh, wait a second. I think I made a mistake here. 1, 2, 3, 4, 5. No, I believe what I did was correct. I counted it correctly. 1, 2, 3, 4, 5. Yeah, no, this is correct. But it's not a perfect square. Because these are not, this is even and this is even, but this is a 5. So that's why this is not a perfect square. I got it. So if I took out the 7 and I took out the 11, that means I took out 2 of the 12. So that means this was length 10. And length 10 doesn't work either. Okay, I got it. I think I'm getting the hang of this now. And then therefore, I've got to get rid of one more 3. Okay, I got it. I understand. Okay, so I'll just get rid of the 3. So that means I'll just be left with 1, 2, 2 to the power 4, that 5, 2 times 3, which is 6, 2 to the power 3, which is 8, 3 to the power 2, which is the 9, 2 times 5, which is the 10, and then the 12, which is 2 to the power 2 times 3. Now let's combine this carefully. Oh, hold on. What did I do here? There's something. This is 2, sorry. How did I get a 4? Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 2 to the power 10. And then 1, 2, 5 to the power of 2. And then 1, 2, 3, 4. There we go. So this is indeed a perfect square because it's essentially 2 to the power 5, 3 to the power 2, 5 to the power of 1, all squared. So there we go. And this was 1, 2, 4, 5, 6, 8, 9, 10, 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9. This was a 9 length is basically 9 terms. Yeah, so I think that's it. So the 9 term Schonk sequence or 9 length, what's the length? A Schonk sequence of length 9 basically is the longest, and 10, 11, and 12 are not possible because of what I've explained there, because of this 7 and this 11. Those have to be taken out, so immediately drops it down to 10. And then 10 gives you this guy here, which because of that exponent cannot be a perfect square, so you got to take out another 3. So you can explain all that in words and it should be sufficient. And finally, a sequence of 4 terms, ABCD, is called a super-duper Schonkolistic sequence, SDSS. Exactly when each of ABCD and ABC and ABCD is a Schonk sequence. Determine the number of pairs Mn such that M1176 N48400 is an SDSS. Okay. So we want ABCD to be an SDSS. Okay. All right. So this is what they've given us. So that basically means that M times 1176 times N times 4840 is some perfect square. And I'll call that whatever you want to call it, K squared. And then the first 3 also are going to combine to give a perfect square. We'll just call that Q squared. And then the last 3 combine also give a perfect square. Yeah, and we'll just call that whatever you want to call it, P squared. Okay, and then the other criteria, of course, is that M is less than 1176, is less than N, is less than 48400. Okay. So which one do you want to work with first here? I think it's better to work with something that only has one variable. So let's go with that one. Okay. So first, let's break all this into prime factorization. 1176 is what? 2 to the power of 3 times 3 to the power of 1 times 7 to the power of 2. And this big 48400 is 2 to the power of 4 times 5 to the power 2 times 11 to the power 2. So if when you combine all these guys, I believe you get 2 to the power of 7 times 3 to the power of 1 times 5 to the power of 2 times 7 to the power of 2 times 11 to the power of 2 times n, and that's got to be a perfect square. Okay. All right. Now what? Okay, so we got to figure out how to make this a perfect square. Perfect square if the exponents are even. So that's even, that's even, that's even. So we've got to have at least a 2 to the power of 1 to make that an 8. This n, for example. And the n also have at least a 3 to the power of 1 in order to make that, combine with that to give 3 to the power of 2. So the n has to have at least a 2 and a 3 in it. So, yeah. It has to have at least a 2 and a 3. And then the rest of the n has to be a perfect square. So whatever you want to call it. I don't know what the rest of the n is. So that means that this is 6t, right? 6t squared. That 6t squared has to satisfy the criteria for n, which is that. That's got to be less, in between 1176 and 48400. Okay, I think I'm getting somewhere here. Okay, so that's good. That's good. Okay, so let's divide through by 6, and when you do, you get 196 here, t squared. And here you get approximately 8066, approximately. And then take the square root, and when you do, you get 14 and approximately 89.8, I think. So therefore, since t has to be integer, t is going to be all the integers in this range. So that's basically everything up until 89, but everything greater than 14. So that, I believe, is 75 values for t. Is that right? 89 minus 14. Yeah. Okay, great. So that means we've got 75 values for n. Okay, great. So that is part of the puzzle. All right, so where do I go from now? Oh, I got to figure out m. Okay, all right, so same kind of principle here. So how do I figure out m? Well, m is basically less than 1176, right? Yeah. And this criteria has to hold true. Let's just this, like, that when you multiply, it's a perfect square. So, oh boy. Okay, I think based on that, let me just use this one here. Let's just write it out here. M times, what's 1176? That's 2 to the power of 3, 3 to the power of 1, 7 to the power of 2. And then this n is what? 6t squared, right? So 6, which is 2 to the power of 1 times 3 to the power of 1 times t squared. And this combines m 2 to the power of 4, 3 to the power of 2, and 7 to the power of 2 t squared. And this is, I've called it q squared. So this is a perfect square right there, because all those exponents are even. So that means m has to be a perfect square in order for this to be valid. So m must be some perfect square, whatever you want to call it. It doesn't really matter, a squared, whatever. So it has to be a perfect square, and it has to be less than 1176. So basically what that means is any perfect square less than 1176. So 1176, the square root of that, I believe, is like 34.3. So any perfect square less than 34.3. So for example, 34 squared, 33 squared, ... all the way down to 1 squared. So this is 34 values. So that means there's 34 values for m. Okay, so we have 34 values for m, 75 values for n. So the total number of of pairs Mn, is it Mn? Yeah, Mn is 34 times 75 because you have 34 values for M and 75 for N. Therefore, this is 2550. And that completes this question.